for giving me the chance to escape from our Basdin business. So today I'd like to talk mainly on Higgs bundles. And let's start from the definition of Higgs bundles. So a Higgs bundle is essentially a vector bundle with a symmetric algebra, symmetric tensor algebra module structure. Or more explicitly, a vector bundle is a Higgs bundle is a pair of E, a vector bundle, and phi, where phi is homomorphism from the tangent bundle to the endomorphism of E, such that for for two elements in tangent bundle, we require that the two homomorphisms are commute. For each two vectors, this must commute. Okay? Or equivalently, this condition is just like this. You can rephrase this condition like this. Namely, phi is homomorphism from E to E tensor omega 1. So this is equivalent here. This is equivalent to the this condition, such that phi, the composition from E to E tensor wedge 2 omega vanishes. So, okay, right. So standard examples of Higgs bundles are these. First of all, examples 1. Let omega be a global one form. And let phi be the map like this, omega x1 tensorized E, defined by this, E to omega tensorized E. So this is just omega times identity. This is, of course, this gives a Higgs bundle, trivial Higgs bundle, not trivial, but elementary Higgs bundle. And example 2 is this. Let consider this E And so let's take the homomorphism of endomorphism, endomorphism of E, which is defined by the multiplication on component this O and 0 on Tx. Or more natural interpretations like this. This is symmetric tensor algebra of tangent bundle modulo this ideal. So, of course, this has a natural symmetric tensor algebra structure, and this is ideal. So this has a natural symmetric tensor module, right? So more general example is just like this symmetric tensor. O plus tangent bundle plus symmetric tensor of tangent 2, tangent plus and so on. This is also Higgs bundle. And its dual is also the Higgs bundle. It's dual, right? In this case, tangent bundle acts on this vector bundle by the contraction map. Contraction. And the fourth example, natural example, is like this. Let's consider a flat, smooth family. Or maybe Y should be okay, better. Smooth, a proper smooth family. Or maybe projective is better. Projective smooth family. Of varieties, and consider vector bundle. Oops, maybe F. A is OX tensorized with R N F star C S U Y. That's a natural Hodge structure. And its graded pieces are of this. Good F is Q F star omega P plus Q 1 N. And there is a natural Kodaira-Spencer map. Oops, Kodaira-Spencer. Which sends R Q F star omega P to home. Q minus or Q plus 1, so F star omega P minus 1. Yeah. So this gives you the this is F, and this determines the structure, Higgs bundle structure of F. F is a Higgs bundle. So these examples are basic ones. And of course, you can define the Higgs subsheaf. As a Higgs sub equal symmetric tensor Tx subsheaves. So in this case, for example, a 4 maybe. In example 4, and if n is 1, then you have this structure, E and R1 F star O. This is natural structure, right? F star omega x modulo, y modulo x. And Godel Spencer map maps this piece to here. So as a Higgs bundle, this piece is a subsheaf. And this is a quotient. So the inclusion relation is reversed, okay? Because this is the phi. So it's a very artificial concept in some sense, okay? In spite of this unnatural definition, still we have Bogomolov inequality. Of for semi-stable Higgs bundle, namely. So of course, semi-stability is defined like this: mu fix an ample line bundle, ample. On X of dimension, say D, and if E is a Higgs bundle, and in general vector bundle, for a vector bundle E, mu of H, mu of E, this is called the slope. Is defined to be this number, rational number, so E times H and D minus 1 divided by the rank of E. And semi-stable means that for every Higgs bundle is semi-stable, if and only if for every Higgs subsheaf E, the slope decreases, namely okay, as usual. A subsheaf means actually full, just a subsheaf. Subsheaf it may not be vector bundle, but torsion free, of course. So rank means, in that case, rank means the rank at the general point. Okay. Sorry? Of course, it's okay, but if we consider quotient, then quotient can be torsion-free, right? Yeah. But of course, subbundle is okay. But anyway, it doesn't make any difference. So, sorry, anyway. Yeah. So, Bogomolov inequality says the following. If E phi is semistable, then C1 of E square to 8G minus 2 is less than or equal to twice rank E. So yeah, and rank E minus 1 times C2 of E. Just the similar inequality for semi-stable vector bundles. Oh, sorry. Of course, here you need HD minus 2. Right. Thank you. So, for example, this is very strange. Anyway, so if let's consider a surface, okay, surface of general type. And consider this tangent bundle plus O plus. So in this case, this is a subsheaf because multiplication of T is maps from here to here, right? So this is a subsheaf. So in this case, of general type and the minimum. And you can easily show that this is stable. This is a stable Higgs bundle. This is subsheaf. And this is quotient. And this is a stable Higgs bundle. So this means that, and this is, of course, the rank is 3. And this means that minus k, C1 square, C1 is just minus k, and C2 is C2 of E. C1E is minus kx, and C2E is just C2 of x. And this Bogomolov inequality means that kx square minus kx square is smaller than, rank is 3, so twice 3, and 3 minus 2, 3 minus 1, so 2, times C2 of x. And this is Miyaoka-Yau inequality, right? So this gives a very strong implication. But the proof is not very elementary, quite different from the usual Bogomolov inequality case. So known proof uses proof of the Bogomolov for Higgs uses, this was proved by Simpson, and the proof was done by using the existence of good metric, good Einstein metric But this is not Einstein, not Hermitian metric, but indefinite metric. Metric on E. And it uses, of course, sort of Monge-Ampere equation, and very complicated. So what I'd like to talk about is elementary proof of this inequality. Not very elementary, but anyway, much easier than original proof. Okay. So what I want to prove is the following. Sorry, this one? This was proved by Simpson, right? Yeah. Yeah. In which year? I forgot. 1980 something. So, algebraic proof of this inequality has been absent for a long time. So what I want to prove is the following. First of all, anyway, there is some generically finite cover. For everything reduces the following case. It's okay here. There exists some generically finite cover. Which satisfies the following, which depends, this depends, depends on structure, x depends on y, depends on x, and the underlying vector bundle structure of E. Not on Higgs bundle structure. Sorry. Oh, yeah. This is just an example. This is example. If you take some base change, then you can easily show that this itself is semistable, kx semistable. Yeah, it's just easy exercise that this is semistable. Yeah. This is smooth. Yeah, this is smooth projective over C. Yeah, and Y also. Y too also. By the way, the Bogomolov inequality is false in positive characteristic. Okay. For instance, in this case, there is some surface genotype on which the Miyaoka-Yau breaks down. This is for general case, yeah. Dimension, just X is projective, smooth. Sorry? I think Hughes semistable, yeah. If it's semistable vector bundle, this inequality is well known for a long time, yeah. Yeah. exactly the same. What I want to prove is this. There is some cover which is determined by x and e such that the induced Higgs bundle structure maybe tensorized with omega y tilde can be deformed to a pi star h semi-stable vector bundle. So if you tensorize with this guy, then this becomes essentially semi-stable. Moreover, maybe not ample, but you can choose the pi that this is ample. Yeah. But essentially, ampleness is not very important. Nef and big is very important, of course. Not finite. Generically finite. Generically finite is surjective. But after going down, why? Yeah. Moreover, for each n symmetric tensor, E tensor, star, this also can be deformed to a semi-stable one. So this means that if you apply Bogomolov inequality, for semi-stable bundles, semi-stable vector bundles, then you can prove that, and if you take n to be to tend to infinity, then you can easily prove that you get Bogomolov inequality for E. And simultaneously, you can also prove the following. Corollary. If E phi is semi-stable, then so is the symmetric tensor phi. Sorry, some sort of this is semi-stable. And in particular, if E phi and if you apply this to E plus E1 plus E2 symmetric tensor, you can prove that if E1 phi 1 and E2 phi 2 are semi-stable, then E tensor, E1 tensor E2 with this structure is again semi-stable. Again, in positive characteristics, this product structure, product property is not preserved. So what is the idea? Sorry? Because you apply this for n is 2 and E is E1, E2, where, no? Actually, yeah, this one. And it's not, yeah, if you can prove this is, if this is not right, you are right. Yes. So well, I have forgot one thing. Actually, this statement was a little bit stronger. So if E is semistable, E phi is semistable, sorry. Semistable, if and only I stated that this is semistable, right? Something like this. Omega 1. Semistable. It can be deformed too, actually. Can be deformed. I mean, in a good way. To semistable one. And this is actually, this is equivalent. So, yeah, I'll explain soon how to construct this deformation. Yeah, eventually. Not first, right? So how to construct? A y ruler and deformation of E, yeah, deformation of vector bundle. So y is constructed like this. Let's take some very large multiple of h and take a Lefschetz pencil. So you get rational map P1. And of course, you have to blow up the base point. And every fiber, of course, general fiber is smooth. And special fiber has just one node. Okay. Sorry. For simplicity, I assume that X is a surface. By taking the general hyperplane cut, you can reduce everything to the surface case. So in this case, general fiber is a smooth curve, and special fiber has just special. It's a nodal curve. Nodal. Yes. So it's if the restricted, of course, the omega, the rank of omega decreases, but still, if you semi-stability is preserved, actually. Yeah. Cutting. No. Just yeah. So actually, this is take the in higher dimension case. So, but taking the Lefschetz pencil operation is compatible with a hyperplane cutting. Okay. So everything commutes, no problem. And consider a double cover here, base change, and this is B and C, Y. This is P1. Take the two fibers and take the two double cover branching along two fibers. Okay. So this variety may be rigid. In general, it has no trivial deformation, but this cover has of course deformation. It deforms because you can change the branch point here. Okay. So let's write down some commutative diagram like this. If the branch point is general, then it's okay. So everything is general, so no problem. So consider the diagram. Yep. So yep. Oops. First of all, we have this one. Tangent bundle of X tilde has a natural omega. Relative tangent bundle. Not bundle, but anyway, B. This is actually, in this case, I should write like this. Relative canonical bundle, inverse, and the quotient is the pullback of omega B. Essentially, the pullback of the base, tangent bundle of base. Okay, and this is not surjective, but if you blow up, replace X tilde by its blow up at the nodes of singular fibers. You get this omega inverse X to the B times exceptional divisor T actually some pullback. of this guy. And you get this guy minus exceptional divisor. And this is surjective. And this is the tangent bundle of tangent y is essentially this is a subsheaf, right? Actually, we have again pulled back this guy to y tilde. So there is a natural map here. And this guy is the same. Y, relative 1 is the same. Exceptional. And of course, this part is different. TC, and this is injection again. Something minus exceptional. Sorry? Y tilde, yeah. This is, yeah, we are working on y tilde. This is this pullback is a blow up. Blow up. Oh, yeah, yeah. Blow up at the node. Okay. Essentially, this is, we don't need this. The important thing is that there is, just looking at this diagram chasing, you can prove that there is some theta in H1 of this guy, the same thing. Y to the C exceptional, 2 exceptional, 2 times exceptional, which is mapped to non-trivially H1 this guy, Ty, in this case, plus exceptional divisor. And this is isomorphic to just this guy, Ty, tilde. And this maps non-trivially non-zero. But if you map to H1 of Tx, actually something pullback of Tx tilde, exceptional. This is zero. Zero map. So some elements is non-trivially mapped here, but trivially here. Just take some element here. Just take the diagram chasing. Actually, construction is the same. Yeah, like this. T Y tilde. Right. This no. The cokernel is 2 fibers, or fiber 1 plus OR2, like this. Yeah, because support on the fibers. And if you take the long cohomology sequence, and then you get H naught of this guy is mapped to this goes to H1 of Tx, Ty tilde, H1 of Tx. So take the two general element of this and consider the image like this. And you can prove that this image is contained here.
Does it come from the H0 of the TV?
Yeah, H0 of TV. Ah, yeah. It comes from the H0 of TV. Yeah, TV. Yes. So I need just plus exceptional divisor to get the H naught. You're right. So now construction of Y is over. Then how I deform E tensors omega, right? So consider theta is locally is a collection of theta, alpha, beta, like this. H naught of U alpha, U beta, and T y. T y something. So, or more better, the image here. You see the bar, right? So this is contained in here, T y tilde. So and you have a morphism E. This is to U alpha or U beta, and to E tensorized with omega, right? Omega Y. This is just the restriction of the original map. Then consider phi. This is just, or this is an extension class of omega Y tilde O. Okay, anyway. So you can consider this. Oops. Omega, sorry. Omega x y tilde tensorized with E. Endomorphism. Non-trivial endomorphism. And consider this map, exponential of this map. This is just sigma I naught this map maps this automorphism. This is an automorphism, and you have to note that the this is automorphism anyway. But in general, this may not be define a cocycle. But however, by the commutativity condition, anyway, phi sigma 1 commutes. Phi eta 2 1. this condition means that this defines a cocycle condition. So exponential phi sigma alpha beta defines a one cocycle. So it defines a patching up of a vector bundle. So you define. So you get some sort of this. Defines a vector bundle. On Y, Judah. Theta 1. So this is a local vector field. If you have a local vector field, then this is an endomorphism, right, of E. Yeah, and these two endomorphisms commute each other. This was the commutative condition of the Higgs bundle, right? Theta. Oh, this, this, because this is, in matrix representation, phi is like this. Phi 1, phi 2, dx, dy, locally. And theta is mapped like this. Theta 1, theta 2, like this. And then this map is just a composite of the phi sigma is just the composite of this matrix. So you compute and this commute. So if you consider this something like this, then you can alpha beta, theta alpha beta, phi theta beta gamma, something like that. This is theta, something like that. Yeah. You need this commutativity condition. So the commutative condition is very essential to construct this vector bundle. And and by many computation, you can prove that this is semi-stable actually. And this was not implicit, but I need a very special property of the cotangent bundle or tangent bundle, actually, because I need what I need is the following property. If you have essentially, if you forget about the blowing up, then this is essentially obtained by branch covering, or blow down of the base point. Branch cover along two elements, L1 and L2, in X. Very ample, right? So the difference of this, actually this is singular, but actually if you consider 4-to-1 cover, first branching here, and then second again here, gives the non-singular variety. So actually take the 4-to-1 cover, set. Then actually maybe it's better to consider everything on this smooth variety. Then you have this is in a compass. X is contained in here, and the cokernel is of course supported by this very ample one. Or actually so Z is This is L1, L2, and this is R1, R2. And then this cokernel is very negative, actually. R1 minus R1 plus. This is a normal bundle. This is, in this case, this is very, very, in some sense, positive. This is actually semi-stable in KZ semi-stable, actually. But this quotient is supported by a very ample divisor, but its quotient is very negative. This is a very special property of omega. For example, if you consider a rank 2 vector bundle, OH plus OH, and consider some vector bundle, the difference is of which the difference is supported by a very ample divisor, then quotient is very ample, very positive. So I need this property to show of course, the semi-stability of this guy. So this the vector bundle, the condition that the vector bundle is omega is very essential. For example, if you so if you this is omega E H plus omega so 2. This is omega H 2 module, right? Tensor symmetric tensor algebra, or minus H is better, maybe minus H. This is this module, right? And this is again semi-stable, this module. But in this case, of course, Bogomolov inequality doesn't hold. In this case, C1 Bogomolov fails. So what I wanted to say was that I really needed the commutative condition of the Hughes bundle, and the module structure was given by a tangent or cotangent bundle. That's all. Well, thank you.
So, are there any questions?